So next, so in the previous problem, we only had convection as a disturbance to the system. In this analysis in section 5.3, we are going to do a very general analysis. We are going to still assume the system is going to behave as a lump, but we are going to have multiple disturbances to the system. We are going to have a constant heat flux, we are going to have convection, radiation, and we also have some generation. So how are we going to analyze this? So how are we going to obtain an expression for temperature as a function of time when you have all of these disturbances happening at the same time? So again, we are strictly sticking to the Lumped capacitance method. We are assuming the Lumped capacitance method is valid. So again, we'll be starting with the energy balance. We have energy in minus energy out plus energy generation is equal to change in the internal energy of the system, which is rho v Cp delta T by delta time, or mCp delta T by delta time. So now we need to express energy in and energy out terms in here. So if you go back to figure here, so we have constant flux coming into the system. Let's say the direction of the arrows are showing the direction of the heat transfer. And in this case, the constant flux is entering into the system. So we need to multiply that flux with the corresponding area for the constant flux. And then we have convection that is leaving out from the system. So convection, and let's say the surface area that corresponds to that side is, let's say, A sub C, that is for convection area. This is for constant heat flux area. So we have convection coming out from the surface on the right hand side. And then we have radiation. And again, this is the area that is corresponding to radiation. So this is the radiation area. And again, they don't need to be equal to each other. So if all of these are given, so you have to treat them differently. So radiation is basically depends on temperature to the fourth power. And let's say then we also have an overall total generation in the system. Again, energy generation is Q dot times V. Q here, energy generation per unit volume. Or if you want to do the integration, so you have Q dot dV. If Q is a function of position, then you need to calculate this way. But if it is uniform, it is basically Q dot times V. And if you have non-uniform Q, again, it will be difficult to justify the Lumped capacitance method. In most cases, you will have a uniform Q for the Lumped capacitance problems. And you can simply calculate it by multiplying volume by Q dot. Okay? So now we have a differential equation. And we have variable t here. And this is a constant. And variable t to the 4, another constant in here. So this is a nonlinear equation because we have t to the 4 terms, and this makes this analysis complicated, and it is not possible to integrate this analytically. So now you can, on theory, you can use numerical methods and solve it if you have all of these forms together. So you have to treat this problem as a numerical analysis problem, and you will solve it. But we have some special cases. In reality, you will never have all of these 4 terms at the same time. So now let's talk about special cases. Let's say we have a situation, we only have radiation and radiative cooling. So we don't have convection, we don't have constant flux, we don't have generation. So this is the equation that describes the Lumped capacitance analysis for the radiation only situation. So what do we have here? So we have change in the internal energy, and here we have cooling due to radiation. So how do we analyze this? How do we carry out this integration? So you rearrange this integration a little bit. So you collect the temperature terms on one side and time term other side, and all of these other variables are constant, so they can be taken out to the integral. And then now what? So you go back to refer to table of integral, and you will see that we have these two integrals, and we can express this difference as t squared minus t surrounding squared multiplied by t squared plus t surrounding squared, and then you separate them in two terms and use this integration tables, and you carry out the integral, and it is going to be this long expression. Again, at this point, I mean, you can even use this in Mathematica if you like. So I'm not going to keep you responsible for carrying out this integration. Again, this has been already analyzed, and the integration is not going to change. So again, all the exams or all the works that you'll be doing is open book. So that means you can take this equation as given. So if you have this integral, if you carry it out, you'll obtain this expression. So the second case is we have a negligible radiation. So we are saying we neglect the radiation and we keep everything else. So this is constant heat flux, and mathematically it's a constant. We have a temperature variation here and another constant here. So we can do the same trick we did in the original analysis, and we introduce a variable theta, which is t minus t infinity. So d theta is equal to dt. So that means d theta by dt is equal to dt by dt. Then with this analysis, we have this simplification. So now I want to divide everything by rho VCP, and these two terms are constant, so they can be considered together, and we divide it by rho VCP, and then we have the other term here. This is due to convection. So if you take a look at this equation more carefully, so we have a constant here, A, another constant here is B. So the form of equation is this. We have d theta by d time, A times theta minus B. And this is an easy integration to do, so we can basically do one more substitution, and we can call theta star as theta minus B over A. So that means d theta star is equal to d theta. So with this substitution, our equation will become in this form. And then you can separate the theta terms on one side and time term on the other side, and then you integrate, and again we saw this already, you are going to get an exponential. So this is going to give you a log term, and this is going to give you minus AT, and then you take the exponent of both sides and you get theta star. And then you can back substitute, use this expression here, back substitute. So we back substitute everything, and this will become our solution. And here A and B are defined as we saw above here. So that will be your expression for temperature as a function of time. Okay, this is the second special case. So another special case, we have convection only. We only have convection. However, in this case, H is a function of time. It's not time, temperature. So this is a situation we have never done, but in chapter 6 and from chapter 8 and 9, we'll be talking about finding the convective transfer coefficient on our own, and we will see H is a function of temperature. And now let's say if we have an empirical expression that describes H as a function of temperature, how do we analyze these problems? So let's say H is a function of temperature and given in this form. Okay, so this is a special case. H is a function of temperature, and I will substitute this expression in here, and I will carry out the integration. So you substitute this term in here, and then you can see you can combine these two terms, and the power will be n plus 1. and then you'll be referring the same thing, t minus t infinity as theta, and d theta is equal to dt, and then you can integrate it. So you can integrate it, and you will be obtaining this expression for temperature.